the key will tell you 1 inch on your ruler will equal 200 miles on the map. Okay? So we use that scale to help us figure distance. Like Madison said, how far is it from one city to another? How wide is a particular state? So they've taken everything and they've shrunken it down to what they call scale. Now, of course, for a map, they're going to shrink it, because if you had a map the same size of Wisconsin, you really wouldn't need the map, now would you? Okay? It'd be kind of hard to see anyway. So yeah, they shrink everything down, but they don't do it like we would. Okay, you know, here's the state of Wisconsin, and we're going to draw that little thing, and that look kind of like Minnesota, or an oven mitt, something. Does it go out like this? Anyway, but they do it by scale. They'll actually shrink it down the right way. Are there any other opportunities that we would use a scale drawing for? Maybe a map is an example of something that has been shrunken down. Is there any example where they might enlarge something for scale drawings? Yeah. Yeah. Sure, it helps you calculate an actual distance, kind of like what we talked about there with the map. Yeah, so you don't actually have to get in your car and drive from one side of the state to the next, or from one city to the next. Okay, it helps you calculate distance. But that's when things get shrunken down. Any example of where maybe they blow something up to scale? Where might you work with something really small where the directions might need to be a little bit bigger for you? Yeah, Brandon. Okay, okay. That could be a possibility, because you think of science, you think of things being microscopic, and they blow it up to kind of see what the relationship is. How about anyone ever work with like models of anything, where you put together models of I don't know, where do you put models together of these days? Yeah, sure, cars, right? So you might be working with some very small parts, and they may blow it up in the direction so you can see it better. Okay, it's a possibility. The whole point is that they don't just do it freehand, and they don't just wing it. When something is drawn to scale, it's drawn as perfectly as possible. It's like a mini representation of what you're actually working with. For example, if we were to take a look at the top of page 291, okay? Take a look at the top of page 291. The best way to explain this is to kind of go for it and just kind of jump you right into a couple of examples. Top of 291 starts with, suppose you are making a model for each item. Use the scale of 1 inch to 9 inches to find the length or height of your model. So your scale and what you're going to use for that particular set of problems is 1 inch to 9 inches, and that's something you want to keep in mind. This is written as a ratio. How is a ratio different than, well, can we write this any other way if it's considered a ratio? What's probably the most common way, or the easiest way for you to see ratios written? Like this, or is there a better way? Yeah, fraction. So let's go ahead and just put that in fraction form. 1 inch to 9 inches, okay? And we use that for any of the ones that would be in that section for 9 through 12. So the first one is a chair. How big do they say the chair is? 36 inches. Now, if we're going to make a model of this chair, we're going to make the model bigger than the chair. Like, you ever go to, is it Steinhoffel's? Out in Waukesha, out in Pewaukee? Did you ever go there? Did you ever see that huge lawn chair that they have sitting out there? They can send me, I'll find a picture of it. They've constructed a huge, like, lawn chair. It's monstrous. I mean, I say big. It's not even just like a little bit big. It's huge. So would they do that if they're going to make a model of the chair, or are they going to make it smaller? Smaller. So the 36 would represent, okay, actual. Actual, we can say, sometimes you say drawing, sometimes we say model. The 1 inch represents the model. The 9 inches represent the actual. So if the actual is 36 inches, what would be the model size for how tall you would make that chair? Now, this is written as a proportion, just like we worked with well before Christmas break. Remember, look for a relationship. How would you get from 9 to 36? Times 4. So then 1 times 4 would make it 4 inches. So your missing value would be the 4. Okay. How about the next one, number 10? A whale is 468 inches long. Again, we'll use the scale. $468, was it? Okay. A little bit bigger. Maybe not as easy to see right away. Then we had a certain kind of routine that we followed when we tried to find the missing value in these proportions. First one was we looked for a relationship. Can you, off the top of your head, tell me 9 times what is 468? No. Second option was to do what? Simplify an existing ratio. Can you simplify 1 inch over 9 inches? No. So the final option, cross multiply, and then divide. 468 times 1. Then divide by the 9. Not 82. Sure, so 9 into 46, 5 times is 45, and 18. So your model of the whale, if it's drawn to, or if it's made to scale, it's going to be 52 inches. So the bigger the actual, the bigger your model is going to be, which should make sense, right? Okay. Try the next one. Number 11. A lizard is 12 inches long. Okay, is the relationship between 9 and 12? Can I multiply 9 times anything obvious to get 12? No. Second option, can I simplify this? No. So final option, cross multiply, 1 times 12, divided by 9. Now you can write it this way, or you can write it that way. Either way is acceptable. I'm going to show you, though, I think this way might be a little bit easier for you. Because written as, what kind of fraction do we call this? Improper. How many times does 9 go into 12? Once, with how many left? 1 and 3/9 becomes 1 and 1/3. This way, we can still come about the right answer, but I'm going to end up with something just a little bit different because, yeah, I'm going to keep getting this repeating decimal. So it's either 1 and 1/3 or 1.3 repeating. Okay? Either way would be acceptable. It means the same thing. 1/3 as a decimal is actually 0.3 repeating. Try number 12. A stop sign is 117 inches tall. $117. All right, Keyshawn, is there a relationship here? Well, there is, but if you don't notice it right away, what do you do? Because you can't simplify. Did you write it like this, or did you put it as an improper? Okay. So then once, and then 27 should give you what? And if we put it right back here, yeah, we're going to say inches. Very good. Okay. Any questions so far? Any questions on that? No? Good. Now, 13 through 18, very similar. Use a map scale of 1 centimeter is equal to 100 kilometers. Okay, that's our scale. And when we use it, you see how using the fraction form can make it just a little bit easier, right? Number 13 says 125 kilometers. Well, where am I putting kilometers? On the top or on the bottom here on my scale? Right here. Bam, right? So that's where I'm going to put my 125. So in this case, I'm going to find out the centimeter, okay, which is fine. So 100 to 125, anything I can do there? Not necessarily. Can I simplify 1 over 100? So cross multiply. 1 times 125 is 125. 125 divided by 100 equals, okay, or when we said 1 times 125 was 125. If I divide by a power of 10, 100 is a power of 10. How many zeros are in 100? 2. If I divide or multiply by a power of 10, all I really have to do is move the decimal. So if I already have 125 and I divide by 100, I would move the decimal in which place? Left or right? Getting smaller, right? Left, how many places if I have 2 zeros? Okay. Is 1.25 the same as 1 1/4? Okay. Now try number 14. 14 is 80 kilometers. Use the same scale. 80. 1 centimeter. And 80. Okay, so there's not a relationship necessarily between the 100 and the 80. So Trinity, I'm going to have to cross multiply and divide. So 80 divided by 100, if I use the decimal way, 2 places to the left makes this what? 0.8. Right? Did you use the fraction way? Fraction way would be this, 80 over 100, simplest form, 4/5. So either one of those would be acceptable. And if you notice, it actually makes sense. If you look at the relationship between the 1 and the 0.8, which one is greater? Is 1 or 0.8 greater? 1. Which one is greater here, the 80 or the 100? Right, so this is 1 full 1, and you get 100. This isn't quite a full centimeter. You don't get quite full 100. Yes, Josiah? Only if you divide by a power of 10. Why is this a power of 10? because it's 10 to the what power? 10 times 10 is 100, right? Okay. You call that a power of 10. It's the only way we can do that. All right. If you multiply by a power of 10, you wouldn't move it to the left. You'd move it to the right. Correct. Okay. Trying to think if there's anything else there. As you look at 15 through 18, are there any there that you would be interested in trying because they might look a little bit more difficult? Or half of this is setting it up. And if you set it up right with your actual scale, everything else just kind of goes into place. And it's just like a regular proportion. You haven't mastered. You have 6-5, right? Okay. Percents, fractions, and decimals. Essentially, we are speaking of the same thing. Because any percent can be put into a fraction, any fraction can be put into a percent. Any decimal can be put into a percent, any percent can be put into a decimal. And you know any fraction can be put as a decimal, any decimal can be put as a fraction. They can all represent the same value, it's just a different way of writing them, okay? So percents to decimals is the first thing we're going to look at. So in your notes, you might want to make yourself a little header that says percents to decimals. So when you need to know how to convert, right there in your notes will be how you do it. So anyone with a percent that they want to see converted to a decimal, taking requests. Sarah. Good. 76%. Okay. Now, when you think of percents, they have a relationship to what bigger number than 76? 100. 100 is also what we call a power of 10. We just had this, right? A power of 10. 10 to the what power is 100? Second. How many zeros in 100? 2. Coincidence? No. Right? So if we're thinking of the relationship between a percent and a decimal, basically what we're going to do is we're going to divide this 76% by 100. When I divided the other problem by 100, all I had to do was move the decimal how many places? 2. And if I'm dividing, which direction, right or left? Left. So as I do that, my 76% becomes 0.76. Well, I mean, if you think about it, that's it. Really, essentially, move decimal 2 places to the left. So if you know your right from your left and you can count to 2, you should be fine. Yes? Well, that's just one part of it. That's just one fraction of it. That's just a percent of what we have to do for today. It's a part. Now, if you think about it, if you were to score 100% on an assignment, you could also say that you had the whole assignment correct. When you think of whole, you think of 1. Okay? If you had a 76%, could you say the same thing? But because 100%, if we convert this to a decimal, and I move my decimal 2 places, equals 1. Like I said, 100%, you had the whole thing correct. Anything less than that, it's going to give you a decimal that's less than 1. 0.76 less than 1 whole. Absolutely. Okay? So percents to decimals, no big deal. What if you have 7.6%? Do the rules change? No! 2 to the left. 2 to the left. Here's my decimal. 1, 2 becomes what, Josiah? Very good. It doesn't change. The 2 is always 2. Doesn't matter where the decimal is. If you had 340%, sure, it's possible. You can have percents larger than 100. You can have them less than 1. Sure. Right? You've seen Maury before, right? I am 340% sure. So if we move it 2 places to the left, 2 places to the left, what do we get? Right. Or 3.4, right? Same thing. The rules don't change. It's always 2 places. So from percent to decimal, it's always 2 places to the left. While we're on it, let's say the opposite. Decimals to percents. No, I mean, did you ever notice that? It's never like 100%. Like, I'm 100% sure. It's always 150%. It's always like 200%. No, not right. I've seen it before. I don't DVR it. I don't. Do I think it's real? No. Give me a decimal. Give me a decimal. Give me a decimal. Trinity. Point 4.6. As a percent, if moving a percent to a decimal, I go to the left. A decimal to a percent, I must go to the right. How many places? 2. 1, 2 equals 4.6 is 460%. 460. I moved it 2 places. It's now there. Okay. Another one. Here's 0.84. As a percent, 2 places to the right becomes 884. 2 places. It's right here. 84%. Always 2. If we have 0.9, again, 1, 2, always 2, becomes 90%. So if we're going to sum this up, we would say move decimal 2 places to the right. Okay, so we've got percents to decimals. We've got decimals to percents. Any questions? The magic number is 2. Okay, now, as we move on, writing percents as, let's put percents as fractions. Okay. So here is, we've gone through 2 sections, right? This is section number 3. Okay, how we convert. Let's take that 76% that we worked with before. Okay. 76% represents only a part. Now, it's a big part, but if you think about what we said before about if you had 100%, you had the whole thing. 76% isn't the whole thing. So the part as in most fractions, isn't it usually set up as part over whole? I mean, that's what makes a fraction a fraction. So if I already know my part, which is 76, and as far as percents go, what's always whole? 100. So for starters, all you have to do is take whatever the percent is and put it over 100. But are we done? Why not? Got to simplify. Okay? So 76 and 100, both divisible by 2, right? So 76 divided by 2, 38. We can simplify more. And 19 over 25. Now, what's going to be the most challenging part for this section, percents as fractions? Remembering to put it in simplest form and not stopping once you get to 38 over 50. So we can take another percent. 60%. For starters, we put 60 over 100. But since they're both divisible by 20, 3 over 5. Now, what do you do in this case? 110%. We're going to take whatever the percent is, which in this case is 110, and we're going to put it over 100. What's different about this fraction than the other ones? Yeah, it's improper, so I'm going to get a mixed number. I still simplify. 100 into 110 is 1. Becomes 1 and? Okay, that's what we're going to be looking for. But like we said before, just as you can have percents that are greater than 100, you can also have them that are less than 1. So if we have 0.5%, we're going to start off by putting that 0.5 over 100. Now, most of the time, when you put a fraction in the simplest form, if possible, that top number, that numerator, can be 1. To get from 0.5 to 1, I multiplied by 2. So if I multiply the top times 2, I would get 1 over 200. See, I can't really keep this here. Why? Why can't I keep the 0.5 there and still call it a fraction in simplest form? Really? Yeah, I can't have a decimal in a fraction. If it were a ratio, that would be different, but it's not a ratio because we're converting it to a fraction. It's either one or the other. Okay, as far as fractions are concerned, you don't have decimals in fractions. It's either one or the other. So you have to make sure you get this to be some kind of a whole number. All right? I don't know how many of these you're going to see, but in case you do, you need to be prepared. So we just did percents as fractions. Let's do fractions as percents. So it looks like the fourth. All right. A fraction. Reasonable fraction. Brandon.
6.
Over 40? let's do a reasonable fraction first, and we'll take other requests that are a little bit more difficult. Willie, 3/6. We'll call that half. Now, most of you probably already know that half is going to be what percent? 50, right. What did we just learn? We just learned that anytime I have a percent, that same number goes over 100. So let's go back here. I need to compare my original fraction to another fraction with 100 as a denominator. Whatever I find up top here will be my percent. Yeah. No practices today. Practice tomorrow. 2 to 100 is times 50. 1 times 50. And since it's over 100, I can call it 50%. 3/4 is my fraction compared to another fraction with what as the denominator? 100. 4 times what is 100? 25. 3 times 25. It is money, right? Quarters. Okay, so if we take a fraction like this, 6/5, still compare it to another fraction with 100 as a denominator, and we just follow the procedure that we have been, noticing that I'm working with an improper fraction. If I'm working with an improper fraction, I should automatically know that what I get up top here is going to be greater than 100. So 5 times 20, 6 times 20 is 120%. Okay? So anytime you want to put a fraction into a percent, you compare it to another fraction with 100 as its denominator. What do you do this one? Step 1, no relationship from 6 to 100. Cannot simplify for step 2, 5/6. The only thing I'm left with is to cross multiply and divide. Put a decimal there just in case. If you need it, it's there. If you don't need it, it's there. It's fine. Doesn't make any difference. 6 into 50 is 8. 6 into 20, 3. Do we need it? You bet. 6 into 20, 3. 6 into 20, 3. What's going to keep happening? Therefore, 83.3 repeating percent. Okay? Look at the relationship between the 5 and the 6. The closer your numerator is to your denominator, the higher your percent is going to be, because it's closer to 100. 5/6 is close to 6/6, not quite. That's why if you had an assignment, there was only 6 problems, and you had 1 wrong, that's why you got a C+, okay, because of the percent. Willie? Why does it have to be behind the decimal? Because whole numbers don't repeat. Okay? Whole numbers stop where? They stop right here. Do decimals have a stopping? Do digits in the decimal places have a stopping point? No. Because this, Willie, is what separates whole numbers from not so whole numbers, right? So that's why we don't repeat whole numbers. Okay? What didn't we cover? Fraction. We cover percents as decimals, fractions as, yeah. Fractions as percents. We just did it. All right. let's see. Let's